The next subject we're going to take a look at is our unified wireless network architecture, really part 2. So in the previous part, we took a look at the need for centralization and the need that we're going to need to manage a great deal of access points with centralized controllers. And we're going to get into the wireless control system, an even higher level of, for sake of fear of redundancy, hierarchy, a little bit later. But first, we want to take a look, a much deeper understanding and view of the wireless LAN controller and the access point becoming associated and being controlled by that wireless LAN controller, or WLC. So looking at some of the phases of the CUWNA, the control and provisioning for wireless access points, formerly known as LWAP, okay, lightweight access point protocol, the access points need to be associated with the WLCs. So they have a few phases. They have their hunting phase. The AP needs to find the WLC. Their join phase. The AP associates securely with the WLC. The authorization phase. The WLC accepts the AP or possibly doesn't. And then the configuration phase. WLC is going to update the iOS firmware and running software on the APs dynamically to what it has installed. This is very similar if you happen to have ever worked with voice. Whenever a phone associates to a Cisco Unified Communication Manager, it updates its firmware because the UCM server has a particular firmware copy for all different types and models of phones. This is the same thing with the WLC. It has firmware basically, or iOS images for each of the different types of access points. And I should note that it has, specifically, it has lightweight access point firmware. Okay, so it doesn't have the full autonomous AP software. We're going to take a brief look at autonomous APs in just a little bit later, a few modules from now, but we really won't be working with them too much. Okay, we'll basically peer inside. We'll understand that it's certainly possible to configure them by themselves. Few different ways, command line and web access of doing so, but 99% of organizations today are doing things, even small organizations are doing things with wireless LAN controllers. And it's also going to, of course, configure the AP with whatever was set to be the configuration on the WLC for that particular AP. So looking at some of the phases of CUWNA, we power on the AP. If there's a static IP address that has not been given yet, the AP is going to do just like any other client, any IP client would do, which is issue a DHCP discovery. It's going to try to get an IP address. Now, something that's deprecated, and I mention it only, we'll look at a few things here in this particular module that are deprecated, that don't really function or are used anymore. The only reason I mention them, really the reason is twofold. One, you might find yourself in a legacy environment that hasn't been updated in some time. Maybe you go to consult for a client and they just haven't done any updates for many, many years now. And so you need to understand, some of the things that could happen. But more importantly, and I don't think that this would happen, but it's still possible, they could test you on some of these older features, seeing that there are still some of these older deployments in the field. So Layer 2 modes is supported. There will be an attempt for a Layer 2 LWAP, wireless LAN or WLC, wireless LAN controller discovery. So basically an Ethernet broadcast. If L2 mode is not supported on the WLC or step 3 fails, which in this case it probably will, most times the APs are going to try a Layer 3, either broadcast or CAPWAP WAN controller discovery. If step 4 fails, they can't discover an AP at all, we're going to return back to step 1. Basically, the AP will reboot and just continue to go in a cycle. Try to get an IP address, try to discover a WLC, reboot, and rinse and repeat. So taking a look at the AP to WLC discovery algorithm, what all we can do to get an access point registered to a WLC. The AP is going to do a CAPWAP discovery broadcast on the local subnet. We already talked about that being deprecated. It actually will still do a broadcast. It's going to be a layer 3 IP broadcast. There is something that was older called OTAP, over-the-air provisioning. I'm going to show briefly in a moment how this used to work. Again, this has been deprecated due to security flaws. Then the AP will sit there and say, hey, do I have any locally stored controller IP addresses? Do I already know in firmware about a previous controller that I was registered to or that I was associated to? I'll try to contact that person. Now, assuming that an AP had been, let's say, resold, used in the field, decommissioned, sold on eBay, bought by someone else, it might have that still in NVRAM, but it will ultimately fail and it will try to find a new association to a new WILC. There is a DHCP vendor-specific option. Okay, so there are some vendor-specific options. These would be how the vendors define them. The RFCs give way for certain vendor-specific attributes, VSAs, in DHCP options. And we'll go over these. These are going to be option 60 and option 43. There's also a possible DNS resolution. One that I don't actually have here is something an IP forward. We're going to go over all these. And again, if the no controller is found, it's going to start over. So let's take a look at a broadcast. So this is actually still how a CAPWAP, really layer 3 IP broadcast would work. I'm sorry, do I have this? Do I have this slide twice? We'll come to it in a moment. So to begin with, the DHCP request is going to be made by the LWAP to try to get an IP address in general. Okay, then it's going to send a broadcast out, and if it does happen to be on the same subnet as a WILC or multiple WILCs, I have WILC 1 and 2 here pictured on the right, then certainly the WILC will respond. Okay, it's a layer 3 IP broadcast. All bits are set to 1, so 255, 255, 255, 255, and it's going to attempt to find a WILC to associate to. Assuming that it's there, it will, the WILCs will respond, and we'll talk about how the AP deals with multiple responses in a moment. Now, what if there is actually a multi-layer switch? So I either have a multi-layer switch, which is pretty much every vendor's Ethernet switch out there today can do layer 3 multi-layer switching, or possibly I have a router. Basically, the idea is that there is a subnet disconnect where we have the WILCs on different subnets than the AP, and we're actually going to show this. We're going to demonstrate this live here in a few moments. What's going to happen? Well, we can't necessarily just send a broadcast through a layer 3 subnet, right? That's the whole idea of subnets and VLANs, is that they define broadcast boundaries. So the broadcast is going to go out, but what we can do is we can issue an IP helper address. Now, you may very well be familiar with IP helper for things like DHCP servers. DHCP is just a broadcast. IP helper is really not specific to DHCP. It is simply a command that says turn a broadcast into a unicast and forward it on to this particular IP address. Now, what does it turn broadcast, or I should say, which type of IP packets does it turn broadcasts into unicasts for? Is it every single broadcast? No. There's another command called the IP forward protocol. Now, there's already a number of default IP forward protocol UDP ports in there, such as those for port 69 for DHCP. DNS is another one, but there's like 6 or 7. But we can go ahead and add to that list. So DHCP is already covered. If I just want to say IP helper address and give it a specific unicast IP address, it will take all broadcasts for all UDP ports that are covered by the IP forward protocol command down here, those default and those explicitly defined, and forward them on to this IP address. Now, if I have multiple IP helper addresses, I can see here I have one for DHCP server, and I have one for WILC number 1 and one for WILC number 2. It will actually forward all broadcasts onto each of those machines. Now, this could be a fine thing. This really probably doesn't have to cause us any trouble, because if we think about it, a DHCP request, and we will talk about how a WILC can be a DHCP server. It's not really meant to be used in the field to scale, except for just, it's basically used for very small deployments. But a WILC can be a DHCP server. But assuming that it's not the DHCP server, and we have a separate independent DHCP server, as we see down here with the IP address scheme, then when a DHCP gets sent, it will get sent to the 10.1.1.1 DHCP server. It will also get sent to the 2 WILC IP addresses. They'll simply ignore it because it's a DHCP request. They, in this example, have their DHCP server engine turned off. They simply will deny, or not deny, but just drop the packet. They'll ignore it. Then when a WILC association request gets broadcast, both the WILCs will hear it, but the DHCP server will also hear it. The DHCP server is not a WILC. It will just ignore it. So it actually really probably doesn't cause too many problems. And I say probably because it really only depends on what particular security policies you might be facing with a given client. Okay, we just need to make sure that we have the proper IP forward protocol. So the old LWAP protocol was 12.222. We talked about how 12.222 and 12.223 were used for data and control. And IP forward protocol 52.46 and 47 were used for CAPWAP. So we need to make sure that we forward 52.46 for CAPWAP. We don't need the 12.222 any longer, unless we happen to have old APs trying to initially start up using old LWAP only firmware images. And then they'll still contact the controller, and the controller will basically update them with newer software, and they will use CAPWAP from there on out. So at any rate, the way it goes, it hits the IP broadcast is sent, the IP helper address turns it into a unicast, forwards it into the 2 WILCs and DHCP server where it's basically ignored. And of course, the WILCs respond back to the lightweight access point. Again, this is just for reference only. This is the old over-the-air provisioning, OTAP, and it was deprecated due to security flaws. But basically the way that this did work, just in case you're ever asked any questions or tested on it, is that if, let's say, we already had an LWAP access point that had already been registered, the idea was that the additional LWAPs that came online could save IP broadcasts over the network or DNS or DHCP requests, in order to, which they'd still have to do a DHCP request anyway to get an IP address to begin with, but be able to save a little bit of bandwidth. And basically, when an LWAP went to say, hey, is anyone else out there that knows of any registered or registerable WILCs, a registered access point with an established CAPWAP tunnel would respond back and say, hey, yeah, I know of some. Here they are. And then the LWAP would try, the lightweight access point would try to register with the WILCs. Okay, so let's take a look at a very valid option, which is DHCP option 43. So the idea here is we're still going to use IP helper address, but just for DHCP server. So it's going to turn the DHCP broadcast into unicast, send it on to the DHCP server, and the DHCP request coming from the LWAP is going to have a particular vendor-specific attribute. And specifically, something called the VCI, the vendor identifier, is going to say always capital C Cisco, space capital A, capital P for AP, space lowercase c, and then the model of the particular access point that's trying to register. So if I have a 1250 series, it will, let's say a 1252, it will say C1250. If I have a 1260 series, it will say Cisco space AP space C1260, and so on and so forth. Okay, basically the first two numbers of the access point are the series number, and the last two are more specific to the functionality. For instance, if it ends in a 2, it's typically 802.11n rated. At any rate, the DHCP server is going to respond back with option 43, giving either a single, or if I have support for an array, it's going to give back possibly multiple IP addresses of those WILCs. Okay, so if you're, again, I'm simply using this because I've talked to a lot of the people that are registered for this class, and I certainly know that voice is fairly prevalent out there, has been around for really longer than Cisco's been dealing with the unified wireless network. So if you happen to be familiar with voice at all, and you are familiar with DHCP option 66 or option 150, both of those are TFTP. Those are industry standard TFTP. They're not vendor specific like these are. It's basically the same idea, is we're telling the endpoint where to go to register and get your configuration. So the lightweight access point will contact both WILCs, and they will respond and will have registration. Another option is DNS request. Now, you might at some point ask me, which one do you think is best? I personally like the IP helper. It's very simple, very easy to use, very easy to deploy. We already use it and are very familiar with it for DHCP requests and forwards to a centralized DHCP server that's not on our subnet. It's just very easy to deploy. The only reason I wouldn't do this is if your corporate policy or your client's corporate policy basically doesn't allow it. With the DNS server option, then, so basically just boiling it down, we have the IP helper address, the DHCP server option, and the DNS server. With the DNS server, the way that this works is we have a DNS request. Now, first of all, I should go back and say there would have already had to have been a DHCP request, right? The LWEP has to have an IP address before he can communicate with anyone and do anything. And watch for security environments where DHCP snooping is turned on. Just make sure that's set up properly. At any rate, the LWAP would have already gotten an IP address, and assuming that there was not an option 43 in that DHCP setup to return the WILC name, there would have had to have been not only the subnet to allow the scope, or subnet to allow IPs to be handed out on, there would have to be a default gateway, and there would normally be a domain name, but more importantly, a name server or a DNS server. So the LWAP would know of a DNS server. It would take that DNS server and it would do a DNS request because it didn't hear anything back from the broadcast. It did not hear anything back from the DHCP server in regard to option 43. So it would make a DNS request called Cisco CapWap controller, Cisco-CapWap controller.local domain. We would have this set up and provisioned already on our corporate DNS server, and we would return the IP address of a WILC, or multiple WILCs. The lightweight access point would, of course, try to go register, and we would assume everything's going to be fine, and they would be registered. So when an AP goes to choose a controller, the AP is going to send a join request message to every WILC which it finds or is, returned a possible response from. It's going to contain an AP hardware version, the version of my own access point, the version of my software, my AP name, the number of radios and the types of radios. So, 3 802.11bg radios and 3 802.11an radios, for instance. And it's also going to contain a certificate payload. The reason for an X509 certificate is so that, and we're going to talk a lot more about this in the security portion, but we're going to talk about the idea of asymmetric keys and the idea of PKI, or public key infrastructure. We're going to talk about public and private key certificates. So the idea of a certificate is that I need to send the WLC, the wireless LAN controller, assuming I'm the AP, my public key so that it can sign all traffic with my public key, and I, with my private key, am the only one that's able to decrypt that. And then it will in turn send me its key, its public key, so that I can encrypt all traffic with its public key, and it's the only one that can decrypt that. And so then we know that any traffic that's sent from me to it and back from it to me is encrypted in such a way that only if I encrypt it for the WLC is the only one that can decrypt it. If the WLC encrypts it for me, I'm the only one that can decrypt it. So this is going to happen so that we can form a transport layer security, TLS, more specifically a datagram transport layer security, DTLS tunnel. And all traffic, not only control traffic and management, but also data that's sent and received from clients through my AP can be sent to the WLC in a very secure, encrypted fashion. And when we take a look at I've said this for a while, but we will, I promise, ultimately get to it. When we take a look at the Wireshark packet capture, you're going to see, other than some of the clear headers, because we don't have wire management frame protection turned on, other than some of the clear headers, we're going to see all the data is basically encrypted, and we have, it's just garbage. Okay, it's really just a bunch of symbols that we can't really make heads or tails of because it is, well, encrypted. We'll also send a test payload to the WLC. The responding controller to the AP request the WLC is going to respond with its controller name and controller type. Is it a 2106? Is it a 2504? Is it a 5508? How many APs that particular WLC can handle, as well as its current load. Something called master controller status that we'll talk about a little bit later. The AP manager IP address. We're going to talk in just a little bit about specific interfaces on the wireless LAN controller, ports and interfaces. And then, of course, the public key. The access point is going to wait for the discovery interval to expire, and then it's going to select a controller based on its list and send a CAPWAP join request. So it's only going to really join one particular wireless LAN controller, but it will do a discovery of all of them, and it will receive a response back. So the AP is going to receive its configuration. After it joins a controller, it's going to move to the image data phase. So the controller is going to upgrade or possibly downgrade the AP. The code is going to be sent in CAPWAP messages. We'll already have a DTLS tunnel. The configuration will then, once it's upgraded or downgraded, be sent to the AP. The AP is going to apply its configuration. Sometimes it will need to reboot depending on various configuration aspects that we'll be taking a look at live in the interface here in a moment. And then basically the process starts over in case there is any thing that hasn't gone properly. If everything went properly and there's no more configuration to be applied, then the AP is up and running. Taking a look at access point as well as wireless LAN controller redundancy, we do have the ability to have multiple APs in a same area. Now, we're going to talk very little bit about planning. We get a lot more into this in the CCNP wireless, specifically the site survey and planning modes, subportion of the class. But we're going to talk a little bit about, and we've already talked about to a brief degree how we want to have non-overlapping channels. Here in a moment, we're going to do kind of a drawing on the screen that's going to give an example of just a very basic layout with multiple cells and even just touch on possible issues, even with a optimally designed network, so that we can then talk about how clean air can take care of some issues and some, possible problems, mitigate some possible problems. But one of the things that we do have the ability to do is have additional APs in the same basic area. Now, you might think, well, wouldn't this cause overlap or noise? Well, it makes the design a lot more complicated, especially when we think not only in a horizontal, but also a vertical 3D environment. But we do actually have the ability, provided we use non-overlapping channels, to have multiple APs, increase the overall throughput, increase the ability to have more clients in a given area, but then also have provisioning for self-healing. So the idea of self-healing is, in fact, let's just go ahead and draw some of this real quick. It will make more sense. So let's use green, and I'm just going to use 3 colors for right now. Remember that I said, and we showed, that the 5 gigahertz band has a lot more available channels. We have 4 channels in Uni 1, 4 channels in Uni 2, 11 non-overlapping channels in Uni 2 Extended or Uni Worldwide, even though I made the argument why we might not want to use them, especially if we're using voice. Cisco recommends against that. I should say voice over wireless. If we're not, then probably okay. And then 4 more channels. So we've got, what, 12. We have, 21 non-overlapping channels. So we're just going to look at 2.4. Whoops. Let's just look at the idea of 2.4 gigahertz, where we know that in the US, we have 3 non-overlapping channels. And those 3 channels are 1, 6, and 11. Okay, so let's just make channel 1 green, channel 6 blue, and channel 11 burnt orange. Okay, so in a normal environment, I might have something like, and this is a perfect environment. Well, actually, my circles are far from perfect, but the idea is that we have a perfect circle, although that's never going to be the case. And we'll talk a little bit later about overlap, how much overlap, and where we want our fall-off dBm ratings to be in order to allow for mobility and roaming. And it's going to actually be slightly different for data versus voice. Voice, we want to have a little bit more overlap and more aggressive roaming so that we have less of a chance for a decreased signal. At any rate, so let's say I'm going to have channel 1 is here. I'm going to have 15% overlap so that I can roam, or 20% overlap with voice for channel 6 here. Now I want to have, let's say, channel, so let's just actually draw the perimeter of a building. And granted, not a perfect building. Okay. So then I might want to have, let's say, orange for my channel 11. AP. So where I have the actual channel here, this is the actual AP in the middle. Okay, so that's my AP for channel 6, my AP for channel 1. Get rid of that line. I don't want that to confuse anyone, but that's the theoretical AP in the middle, or actually it's the physical AP in the middle. The line around it is the theoretical cell, again, not being 100% perfect. And then I'm going to have overlap here for channel 1 again. Now, the idea is not to let these two really overlap. There is overlap for a client that happens to be roaming in this area. Just build those lines again. The client, let's just say the client is magenta, or sorry, violet. The client is, let's say, here, and they're walking over. They're going to have an overlap with channel 6 there. As they walk over here, they have a channel overlap with channel 11, 1, and 6. So they can associate when that client happens to be right there, whether they stop or whether they're moving through, they have the ability to hear and possibly associate with all three of these access points. And then depending on where they actually walk towards, if they end up walking over here, then they make their association with this particular channel 6 AP. Okay, so then I continue to go on out and I continue to draw. Here's an AP for channel 6 again. Here's another AP for channel 11 again. My bad circles, by the way, might actually be a bit more representative of actual radio spillage over into, or radiation, I should say, out from the antenna. Because again, it is not going to be perfect. And especially even if I tune the power down to as low, maybe not as low as I can, but very low milliwatts, I am going to, at any possible point, end up sending a signal probably farther than I want to. Some vendors claim to be able to use beamforming to send the signal exactly and only where the clients are. However, in real life, in pragmatic situations, this proves to be a little bit more difficult than they state, simply because there are typically clients everywhere within, or at least many places, and roaming around many places within these cells. So even if they're beamforming or using those spatially diverse antennas to send the signal to very specific locations, even without that particular type of antenna, using what we talked about earlier, beamforming, to get that kind of radiation pattern, then the problem is they're sending it over here. Ruckus Networks is one that I'm thinking of that claims to be able to do this, and I'm not saying it's bad, it's a good idea, but there happens to be clients over there, clients over here, clients over there. So even with their beamforming and only sending the pattern where they claim is absolutely needed, it happens to absolutely be needed in very many areas due to so many clients around in that the vicinity or the capabilities of that wireless radio and antenna. So watch out for people's claims. Cisco as well. Really no one can do this particularly perfectly, although there are many vendors, really just many advancements in technology, radio technology, that are making it better and better every day, but again, not perfect. So in other words, what I mean by that, just to be clear for those of you that are very new to this, is even though, let's say this channel 1, I show it non-overlapping, and I've done my best with my, what we'll talk about later, my WCS, my wireless control system, to do the planning, even with my site survey, to get as best as I can, as close as I can to not allowing these cells to overlap by tuning the power down. There is going to be the possibility, maybe this particular cell is what I'm going to call the edge of this cell that I have depicted by this green line for channel 1 is going to be, let's say, negative, for voice, it would be negative 67 dBm. Okay? That is anything higher than negative 67. If I go to negative 70 or negative 80, let's say negative 70, negative 73, I still have a decent enough signal for data, but I want to force the client to roam after the cell edge of negative 67 dBm RSSI. We're not talking about signal to noise ratio. We're just talking about RSSI. And the reason I want them to do this is I want them to have a extremely high quality signal. And when they roam, I want them to roam before that signal degrades down to a decreased data rate with dynamic rate shifting, down to something that is going to cause negligible voice quality or video quality. And so that's why I might tune my radio down and set my roaming parameters on my wireless LAN controller down to a, what we'll call a cell edge of negative 67 dB. So that's this thicker green line. Really, the entire line around will be negative 67 dB. Now, the problem is, and let's say this all of these cell edges are tuned to negative 67 dB. The problem is we actually do still have bleed out. This guy can still hear, let's say, negative 85 dB or negative 90 dB. Negative 90, I think, is actually used for the sensitivity setting of the radio, but negative 85, negative 88 dB as we get down there. Okay, so there is still some co-channel interference. Remember, we talked about co-channel interference and adjacent channel interference. Let's just do a quick recap. What's co-channel interference? That's when two channels that are the exact same channel are heard by one another. Adjacent channel interference is not, in fact, I'll use red to indicate that it is not this overlap here. That is not adjacent channel interference because channel 1 and 6 are non-overlapping channels. They don't share any of the same bandwidth, the 20 megahertz bandwidth. If I had channel 5 over here, that would be adjacent channel interference to 1. Okay? So that would be the bad thing right there. So at any rate, getting back to what I was saying about redundancy. We hadn't really had this particular discussion on very basic planning in order to see an example of a we'll take a look specifically at a heat map later, which is similar to this, but done through the wireless control system automated planning. But we hadn't even taken a look at the basic planning idea of non-overlapping channels. Okay, channel 1, as I continue to go out, channel 6. So even with 3 non-overlapping channels, I do certainly have the ability, in a rough way, to create non-overlapping access points that create a full coverage. If I need something over here, then I'll do that. Okay, so with AP redundancy, let's say and this gets into very difficult planning, but it is possible, and it's simply something that you need to know about. I do have the ability to put in, especially if I'm not using, or actually, especially if I'm using the 5 gigahertz range where I have many more, 21 non-overlapping channels, I'm going to have a lot more leniency with being able to do this. But just for the sake of demonstration, since I already have this drawn out, pretend that these deployments of each access point and the channels and the reach of the range of the radio, the radiation of the radio and the antenna is perfect. Just pretend that, okay, for a moment, and then realize you'd use the 5 gigahertz. I can put another AP here that's on channel 1. Again, we'd use the 5 gigahertz range. And I've got my AP that's on channel 11. They're right next to each other. They're on top of each other practically. They're right next to each other, let's say mounted on the ceiling, upside down, maybe above the ceiling tiles, as long as they're properly spaced away from metal objects like steel beams or girders or what have you. And they have the proper patch antennas or whatever omnidirectional antennas probably for this particular, if we're mounting upside down, for this particular cell. The idea is that I've got now double the bandwidth. Now, it doesn't mean that I have double the bandwidth for one client, but I have double the overall available bandwidth. I now have the ability to speak to 2 people at once because each radio can speak to one client or one person at one time. Okay? Should have drawn that one in green. So this can speak to this client over here. The orange can speak to someone else. Not only that, but if, let's say, the orange dies, it goes away, then the green, the channel 1 radio, can take over and essentially self-heal that particular area on the map. So that's what we mean when we're talking about, getting finally back to what we were originally talking about, getting back to talking about self-healing and increasing power levels, basically being able to double the effective throughput, not for one client, but for multiple. They have to be in something called the same RF domain to really allow this to work. We're going to talk about the RF domain in the we'll see in a moment. Looking at controller redundancy, we have the ability to have primary, secondary, and tertiary controllers. So first, second, and third. We do have the ability to use link aggregation to give your controllers redundancy for their physical ports back to the cable plant. And if we're looking at this back into a larger environment of the, looking at the larger wired Cisco environment, we have the ability to use, let's say 3750s that are stacked, and so use multi-channel, multi-chassis ether channel, or more probably, actually that probably would be what we're using it out at the edge for 3750 stacking. Or I've certainly worked with a lot of clients that use 6500s in the access closet. And if we use the newest code and newest 6500s, we have the ability, or even Nexus, we have the ability to have multi-chassis ether channel with the VSS. Okay, so we're now talking about redundancy of physical wires, redundancy of physical devices. We've got really nth degree of redundancy, as much as we need. Okay, we can configure our controller with multiple AP managers so that we have those WILCs able to connect, redundant interfaces with which to connect to. And we can always have a primary and a backup port on the controller. We'll talk about the ports in a moment. Common designs for controller redundancy are either N+1, N+N, or N+N+1. So N+1 is that the N is the wireless LAN controller. We have a single backup for multiple controllers. So I might have, for instance, WILC1 and WILC2, and they each have the backup of WILC3. So WILC1 has a backup of WILC3 only, and WILC2 has a backup of WILC3 only. We also have the idea of N+N. So WILC1 backs up WILC2, and WILC2 backs up WILC1. So WILC1 is primary, WILC2 is secondary, and then we also have APs associated to WILC2 as primary with WILC1 as the backup. Now, one of the things that we need to keep in mind with this particular deployment is that we need to make sure that each WILC has the proper licensing to be able to handle not only their own normally registered APs, as well as the APs belonging to their partner controller in case that particular controller would fail. The design would be no good if, let's say, WILC1 failed, WILC2 took over and took over as not only handling all of its own WILC2's APs, but also WILC1's APs, but it was already maxed out with licenses. It wouldn't work. So you have to watch for that. And then there's also N+N+1. So WILC, in fact, let's just draw this real quick. Okay, so we've got our APs down here. With 3 radios, or maybe 6. We've got WILC1. We've got WILC2. And we've got WILC3. So design 1 calls for N+1. So let's use green as my primary path. So that, actually, you know what? Let's use 3 different APs to demonstrate the 3 different models. So N+1, I basically have my primary path and my secondary path. Okay, the second design we'll look at with AP2 is that, actually, I kind of do need 2 APs for that particular one. So I'll draw that back. So the design with AP2 is I have WILC1, and this guy over here is associated to WILC2. And then they back each other up. So my failover is here, and this failover is here. And then the design with 3 is I have WILC2 as my primary, WILC1 as my secondary, and WILC3 as my tertiary. Okay, so this would be the N plus N plus 1 model. Okay, N plus N plus 1 model. So this would be N plus 1. This would be N plus N. So 2 backing each other up. And then the N plus N plus 1 model, where they're backing each other up, but then there is also a ultimate failover. Again, you just have to watch for licensing and make sure that you're not overutilizing your licensing. We're going to talk real briefly about, if I can get this back, about the modes that the APs can be deployed in. And then we're going to take a break and we'll begin taking a look at a few other things, and then we'll very quickly get into the actual interface. So the modes that the access points can be deployed in, there's a few different modes. The first is the local mode. This is business as usual. Okay, this is the normal, what most of your APs will be deployed as. The AP handles the user data. Really through a CAPWAP tunnel, sends it to the WILC. The WILC bridges between the wired and the wireless. It can provide, the AP in this particular deployment mode can provide monitoring services, can identify some IDS signature matches. If I have a WIPS, a wireless intrusion protection system, it can obviously do management frame scanning, and this mode can be used for site surveys. Okay, so I'm going to be deploying not all of my APs in the same mode. I'm going to have most of them are going to be in local mode. I might have a few of them in monitor mode. Some in monitor mode, these are passive access points. Okay, so they are not necessarily broadcasting on any channel, so I don't necessarily have to worry about overlap. They're basically just listening. They're just passive. They're just listening. So they're used for detecting rogue APs. They're used a lot more for detecting intrusion detection system or IDS signature matching. They're certainly used for troubleshooting, and they're used some for location-based services. Occasionally, I'll want to put something, an AP, into sniffer mode. And again, all this is done from the WILC. And every time I change the mode of an AP, by the way, it applies its configuration. It pushes the configuration down, and then it tells the AP to reboot. The AP has to reboot. But the AP can operate with certain sniffer devices, such as Wireshark or Omnipeak or Air Magnet. So you're basically turning the access point into nothing more than a remote wireless network card, listening. In an area that you can't be in. Maybe you're in a different part of the building. Maybe you're in a different part of the world, and you just want to capture particular data about that cell, that range that AP and antenna can hear in that particular part of whatever building, of whatever office you have. The AP is going to send the data to the controller, and then from the controller, of course, it's sent to the sniffer. Everything's sent through CAPWAP to the controller. We can gather timestamps, signal strength, packet size, signal to noise ratio, something we haven't mentioned yet called SINR, signal to interference noise ratio. Can gather all that information. There's also something called rogue detection mode. Okay, so this is basically the radios are turned off, and what they're used for is, so if the radios are turned off, what are they used for? Well, they're used for listening on that local switch that they happen to be connected to. This is kind of an expensive mechanism, since the radio, what it's built to do, send and receive radio waves, is turned off. But it's basically listening for ARP messages on the wired switch network. And it's because ARP is going to be broadcast, and it's going to compare to rogue APs and client MAC address lists. So this is used for closer pinpointing rogue APs, rogue access points, basically a security threat that we're going to talk about later, where let's say, for instance, I have a very tightly controlled corporate enterprise environment and somebody needs to use their, iPad to, get something back and forth or whatever, send and receive a file or read a file, watch a movie, whatever it is, something that they basically can't do through the corporate network. The corporate network has not yet embraced BYOD, or bring your own device, has not yet allowed anyone to put any devices other than those that IT approves onto the network. So somebody says, well, that's no problem. I'm going to run down to Best Buy or Fry's. I'm going to buy a $40 access point. I'm going to plug it into Ethernet here on my desk. I'm going to hide it, and I'll be able to go outside to an area that's not covered by wireless, right outside my window, and use my laptop or iPad to get some work done at lunch. The problem is you're exposing a huge security hole into your network. That's a rogue AP, and it's something that is very critical and very important to detect and eradicate on corporate wireless networks. The AP can be put into rogue detection mode, turn the radio off, and listen to ARP to deal with that and try to mitigate against that. Okay, there's also bridge mode. We have the ability to deal with bridging between ourselves and other access points. Okay, this is used for strictly old bridge mode, or what we tend to use it for today is mesh networks. So we also can allow for client access. This can be point-to-point bridge, like let's say we talked about on the top of a building with very directional antennas, or maybe even mesh networks indoors in, let's say, maybe a factory floor environment where there is a great difficulty in getting, for whatever reason, Ethernet out to the individual areas that we're going to want to have access point and wireless coverage. We can, a lot of times it actually is easier to, I think, get Ethernet out to an area than it is to get AC power, especially because we can do power over Ethernet. And they're not as, we don't have to necessarily put Ethernet in at least according to most US building code, we don't have to put Ethernet in a metal tube type of a channel in order to run that, whereas we do with AC power. But for whatever reason, there are certainly environments where we can get AC power to a access point. Outdoor environments are much more likely to be used. Let's say a college campus, a university campus, or even a corporate campus network. The outdoor environment, we can get AC power. Maybe there's already AC power on a light pole out near a parking lot or under a bench, in a park type area provided by the corporate. So we can get AC power, but we can't necessarily easily run Ethernet. We can use mesh mode, and that's what this bridge mode is for. There's also HREAP mode. Okay, so hybrid REAP, as we talked about yesterday, is now called Flex Connect. Still does a lot of the same things. It's basically rebranded because it has gotten some newer features, and Cisco also wanted to give it a kind of a newer, flashier name that made a little bit more sense to people. HREAP didn't really make that much sense. For a while, they called it Office Extend. So they called it HREAP, then HREAP Office Extend, and now it's called Flex Connect Office Extend mode. So here, the controller and the AP are separated by a WAN. There are some minimum requirements. The link can't be slower than 128K. The round trip time can't be more than 100 milliseconds. And we have to actually update the AP with certain code. It has to reboot. And we have different modes for this. In fact, we're going to take a look at the comparisons of some of these operations. We're going to talk about split MAC, basically when the WAN is up and when the WAN is down. Because if the WAN is down and the AP normally tunnels all of its information back to the controller, or at least part of its information, what we're going to take a look at here in a moment, then what happens when the WAN's down? We can't connect or can't contact the controller. What do we do then? So first of all, when the WAN is up, We're going to take a look at something called, and this is for HREAP or for Office Extend for Flex Connect, however you want to refer to it. And Flex Connect is with the new 7.2 code. So if you're on 7.0 and older, it's still called HREAP Office Extend. But we want to take a look at something called the split MAC operation. The idea is that we're splitting 802 protocols between the AP and the controller. So the AP is going to handle certain packets autonomously, or I should say switch them out to the network there locally, and then it's going to tunnel some of those packets back over the CAPWAP DTLS tunnel back to the wireless LAN controller. So the AP is going to handle the time-sensitive packets like frame exchange and handshake between clients, transmit beacons, power save mode, responds to probe requests, real-time quality information to the controller, and monitoring for noise. So it's going to deal with those there locally. It's kind of putting some of the intelligence back into the AP instead of making it a completely dumb radio-only device. The controller is going to handle things like association to clients. We're not talking about APs, but to clients. Reassociation when we do something we're about to talk about called roaming. Authentication, what we'll talk about in security. And then also frame translation and frame bridging. Okay, so frame translation, frame bridging. We already talked about the 802.11 frame to the 802.3 Ethernet frame, in terms of the translation and bridging between those two disparate mediums. Okay, and finally, I just have a quick slide. We've already alluded to it many times, but I just wanted to include it in the overall Part 1 and Part 2 of the Cisco Unified Wireless Network Architecture. We already talked about it in Part 1, the need for this, but we have something called the Wireless Control System and Wireless Control System Navigator. We also have a mobility services engine. This used to be called a location appliance, so that's the reason I still have it called location/mobility appliance. You might even have an older location appliance. It can't do all of the things that the new MSE, mobility services engine, can do, but it can do some of them. Okay, this is for the mobility is for much greater tracking of RFID tags for individual clients and particular wireless devices around the network. It's also specifically the MSE, not the location appliance, but the mobility services engine is a critical component along with WCS in the Cisco Clean Air initiative. So the idea there that if we have interference or a rogue AP, let's say we have a rogue AP, the other APs, depending on the modes that they're in, can hear that AP broadcasting and sending out packets and beacons and probes, and it can basically the WCS will coordinate with the APs, send that information back over to the mobility services engine, which runs advanced algorithms and sends that information back to WCS, and on what's called a heat map, we can actually, and these heat maps are generated, we first upload blueprints to the building, literally floor plans, and then we tell the WCS, on a kind of moving map, we sit there and position where our actual access points are physically located on that PDF or CAD drawing of the floor plan, of the blueprint. And then based on all of the RSSI, signal to noise ratio, signal to interference noise ratio, the WCS runs algorithms and builds a literal heat map of different channels and even where clients are, especially with the mobility services engine. It can get very detailed, and it can tell you, like I said, within about a meter of accuracy where a particular client is, or in the case of, let's say, a rogue AP, an access point that someone bought at Fry's and put on the network themselves, tell you exactly where that's at in your network, and then you can go and eliminate that. Or maybe where somebody, maybe a security guard out front who thinks he's doing his job, went and bought some cheap 2.4 gigahertz wireless cameras off the internet and has 3 or 4 of them placed strategically around the front, lobby and maybe some back shipping loading dock doors because he's trying to catch someone who's been stealing something. So he thinks he's doing a good thing when in reality, maybe he is partially doing a good thing, but he's also severely disrupting wireless communication. That's part of what Cisco Clean Air can do. Is it, for one, it can actually dynamically change channels on access points in that area to avoid the channels that are being usurped by those video monitors, those video cameras. But it can also, with the mobility services engine, very accurately pinpoint exactly where that camera is wirelessly transmitting. So that's why we would have things in, let's say, our rogue detection mode, but more importantly, maybe our monitor. There we go. Our monitor mode. Okay, so just passively listening to everything. So that's going to help us be able to go and find within a, very small area, meter, 3 feet, somewhere roughly around there, exactly where these, 2 or 3 different video cameras that he got and someone else's rogue access point is. So all of these things aren't simply servers and additional access points so that Cisco can make money. Certainly they are that. Cisco's a business, but they are actually there intended for a purpose. We're not just overwhelming the client with all these APs and servers for no reason. And we'll take a look. There's also security appliances. So as I alluded to, we have the WIPS, the Wireless Intrusion Protection System. And we also have something called the ISE, the Identity Services Engine. These are things that are outside the scope of this particular course, but those are products that you can look into and will make your network much more robust. By the way, since I'm on the slide just mentioning, and we do have a live WCS system we'll be taking a look at in conjunction with our wireless LAN controllers, adding our wireless LAN controllers, seeing and being able to provision our access points from there, and even live being able to take a look at Clean Air. We will be able to do all that here. I don't have the mobility services engine in this location. We have one, I just don't have it right now, but that's okay because I don't really have my APs spread out in a wide enough pattern. I only have kind of a small 100 square foot office. I don't have it enough in a wide enough pattern that it would really make all that big of a difference. At any rate, when we take a look at the WCS, the wireless control system, there is something that Cisco now calls Cisco Prime NCS. Okay, Cisco Prime Network Control System. This is based on the wireless control system. This is really wireless control system, almost 8.0, if you will. It's the next version. It's the evolution of wireless control system. And the idea is that it handles and aggregates all the information not only from your wireless control, but also from your wired network environment. It also takes into account ACS. If you're familiar with any of the aspects of Cisco security, the Cisco ACS server or access control server is basically a AAA server. Authentication, authorization, and accounting. And it can take into account 802.1x requests from wired, from wireless. It basically aggregates all this information together, or at least attempts to, and gives you a unified picture of your wired and wireless network. So if you've heard of Cisco Prime or Prime NCS, that is the WCS next evolution. So let's go take a look at Cisco.com for a few different things. First of all, let's look at the Flex Connect. Okay, so this is, as I mentioned, HREAP mode. Whoops. So HREAP mode or Office Extend. Okay. And the idea is that, and it can be supported on these particular access points only, these wireless LAN controllers, so not the 2100. We're going to be using a 2106, which is a little bit older, but we're still running 7.0 code. We don't have the option of running 7.2 code. But it can be used on the 2504, the 4404 or 4408. That's an older but very powerful wireless LAN controller. It's the predecessor to the 5508 and the Cisco Flex 7500 Cloud Director that we looked at. It can be run on the 6500 WISM Blade wireless services module and WISM 2. There's actually, it's end of sale, but you were able to purchase a Cisco 3750 switch that actually had an integrated wireless LAN controller in the switch. And then the network module for the ISR, specifically the SRE, the Service Ready Engine. So we have something called WAN up central switching and WAN up local switching. The idea is that with the WAN up central switching, everything's being tunneled back to the WILSI and switched centrally. When the WAN is up with local switching mode, the WAN is up, but the AP is not tunneling all of the client data back to the centralized controller. It's switching it out there locally on its local Ethernet switch. So what's the difference? With WAN up central switching, we're still sending everything out of the AP onto the 10100 or 1000 port, probably 100, 1000 port, the Ethernet, but it's being sent in a DTLS encrypted CAPWAP tunnel back to this central controller. Then the controller does the frame bridging. With WAN up local switching, we don't tunnel everything back in CAPWAP. The AP does the frame bridging and frame translation between 802.11 and 802.3. And then we also have WAN down, where it's standalone mode. And this certainly does switch everything there locally. It has to. Even the old HREAP mode had to have a WAN down possibility, okay? Because the WAN might be down and we might not have a particular wireless LAN controller to go to. If the office is sufficient enough size, that's what this is for. The network module, or really the Service Ready Engine service module with a reduced wireless LAN controller there on that, that's there for remote offices. But when you only have maybe one AP and 5 users out at a remote office, it doesn't always justify the cost of one of those Service Ready engines. Okay, but these are some of the features. And again, all you actually have to do is Google, sorry about this, Google Flex Connect feature matrix, and you'll be able to find this. But it's actually, if I just want to look at the hierarchy, it's under support, specifically product support for wireless, Cisco 5500 series wireless controller, troubleshooting and alerts, troubleshooting tech notes, and under that hierarchy, you'll find Flex Connect feature matrix, or you can just Google that. You'll be able to see what security for the client, security for the infrastructure is supported in each of the 3 various modes that we just talked about. For infrastructure is things like adaptive wireless intrusion protection system. That's up for WAN central and WAN local, not when the WAN is down. IDS detection, management frame protection, okay, the secure services client. There's a lot of things in here. We're not going to go over every single thing because it goes down and on and on and on. But you can read through that and see which features are supported in each mode. And I would recommend knowing that at least having a general overview. You know, if there's something that we haven't talked about, you know, let's say we're going to mention web authentication proxy in a little bit. So I guess that's not, you know, we're not going to go into multicast optimization in this CCNA class. So for instance, if there's something that we don't necessarily talk about in this class, then you probably don't have to worry too much about it. But it's a good idea to have a general idea of the 3 modes and what's supported on each. So let's take a look at Cisco products and services wireless. And we're going to go down and look at network management. And here we have the Prime network control system. This is the new, like I said, evolution of the wireless control system. They do still sell the wireless control system and navigator so that we can simplify management of geographically dispersed WCSs. The Navigator supports up to 20 WCSs and up to 30,000 APs. The WCS, if we click on this, and let's actually just go to the data sheet. By the way, there was an example of what I had been talking about, and I believe I already have one created. It's not going to show me that on the picture. I thought it was going to give me a bigger picture. Normally it does. But anyhow, let me just zoom in here real quick so I can complete that thought. There's an example of a heat map. It's a bad resolution. We'll take a look at a much better one later. But up here, this color bar is really an RSSI color lookup. So the closer to red that we see, that's the highest intensity of heat, or basically the highest and best RSSI signal. As we get out from that, we see yellow. And the yellow, and then even into the green, is really where we have, the green and the blue is where we have good coverage. And these can actually, if we mouse over these in the actual heat map, it can show us the AP name, the AP MAC address, the BSS ID, and the IP address, but it can also show us the channel that it's broadcasting on. And if it has dual radios, possibly broadcasting on dual frequencies, what channels it's broadcasting on. Okay, and so with being able to do that, we can see a coverage area where there's superb coverage, which is the yellow. The red, very few people are walking in the red area. Okay, so that's insanely superb coverage, but the yellow is superb coverage, the green is decently good coverage, and the blue gets out to nominal coverage. And we can adjust transmitter power. We can also allow RRM to dynamically do this. There's a lot of things that we can do, but that's what I was referring to when I was saying a heat map. So anyway, let's take a look at the data sheet for the wireless control system. It would be a good idea to not only know the WCS data sheet, but also the licensing. Okay, you might get asked about how the licensing is done, and there's really, three main models. You've got the single server base and plus, and then you've got the enterprise plus licensing. But know how that licensing works. The base, for instance, will only allow a single server and the base features. It doesn't allow high availability. It doesn't allow mobility services engine. It doesn't allow context-aware tracking like the Plus version does. And it also tells you that I can order this in a quantity of 50, 100, or 500 access points. So one server that would support up to 500 APs. The enterprise version will go up to 50,000 APs. Okay, so know that. Here's an example of the heat map here. In fact, let's just pull up the PDF. Here's kind of a better example of just the dashboard. We're going to actually get into this anyway. I think I have the heat map still saved for my last planning session on this particular laptop that I'm broadcasting on. If not, I'll get it tomorrow for you. But I believe I have that. So anyway, just an example of some of the things the ways that it works. Take a look through this. Take a look through, let's see, is there anything that I want to point out specifically here? I mainly wanted to point out things like the licensing. We're going to be taking a look at clean air with air quality. So yeah, I would say look at some of these talking points down here in terms of what it can go into, but mainly know how the licensing works in terms of how many APs that a single server or enterprise multiple servers can handle.